Double angle identities. Double angle identities are special cases of sum identities when the two angles are equal. If we double an angle of measure alpha, the new angle will have a measure of 2 alpha. So for instance, here's the quick proof of one of our most basic double angle identities. I have the the identity for the sum identity for sine. Sine of alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. Let's have this special case where alpha equals beta. So we'll have two alphas in the middle, right in the brackets there. Sine of alpha plus alpha equals sine of alpha cosine of alpha plus cosine of alpha sine of alpha. Well, if you look here, these are the same terms, right? So we can add them up and put a coefficient of 2 in the front. And we can simplify this further and say that's sine of 2 alpha. This is our double angle identity for sine. And as you might have guessed, we have a double angle identity for cosine and tangent as well. I'll do a different video, a separate video that will show, I'll show this proof again and the proof for the cosine and the tangent variant. Also, there are different versions that if we use the other the other identities for the Pythagorean identities, we can get two more versions of the cosine double angle identity. So two more versions beyond just the standard one. Okay, so these are on your formula sheet. Here's an important note, the argument. So the argument, this is the argument here. Argument. The argument for each double angle identity is 2 alpha. The only way to change the argument is by applying one of the double angle identities. So just remember that. Okay, let's do a couple of examples. Okay, example 4. Write double angle identities for the following. Sine of 10 alpha. So what I'm going to do, folks, is I can think of it like this. Sine of 2 times 5 alpha, right? So I can split it up like that. I know my double angle identity is like this. Normally it's sine of 2 alpha equals, sine of 2a equals 2 sine of a cosine of a. Well, instead of an a, I have a 5a, so I'm just going to plug in 5a. So sine of 2 times 5a equals 2 sine of 5a cosine of 5a. And that's it. That's how to write a double angle identity. Okay, letter B. Cosine of 3x. Oh, I have an odd number this time. I can't just do, well, can I do 2 times? Sure, let's think about it. So cosine of 3x. Hang on. I have cosine of 3x. How can I write that in terms of a double angle identity, right? So what if I do this? Cosine of 2 times what gets you 3x? Well, that's 3x over 2. Okay, and then here's my cosine version of my identity. Cosine of 2a equals, I'm just going to use that first variant, cosine squared of a minus sine squared of a. Okay, wherever I see an a, I'm going to substitute a 3/2 x. So I have cosine of 2 times 3/2 x equals cosine squared of 3/2 x minus sine squared of 3/2 x. Okay, good so far. And then let's that's, well, I guess I can do this, cosine of 3x, just to show that the final value is the same. Okay, there you go. And then this one, let me just say sine of 10a equals 2 sine of 5a cosine of 5a. All right. Last one here, tangent of k. Well, how can I show tangent of k in terms of a double angle? Well, you know I can do this, right? Tangent of 2 times k over 2. Okay, and then I know that my angle identity, tangent of 2a, equals what? 2 tangent of a divided by 1 minus tangent squared of a, so that tangent of 2 k over 2 equals 2 tangent of k over 2 divided by 1 minus tangent squared of k over 2. And let me just simplify this left side. That's just tangent of k equals all of this again. All right, so writing double angle identities for 3 basic terms here. Okay, example 5. Write each expression as a single trigonometric function. So what this looks like is, here we went from double angle to the identity itself, so we expanded it out. This one, I'm giving you the expanded version, or the identity, a form of the identity itself, and I'm asking you to work backwards to get a single trigonometric function. Okay, so let's start with A. 2 sine of 4x cosine of 4x. So let me do this. Kind of like when we did function transformations and you wanted to see what parameters were changing in your transformations, I stacked the two equations so I can vertically look to see what's affected. I'm going to do the same thing here. So I have sine I have sine of 2a equals 2 sine of a cosine of a. Okay, when I look at this, I have 4x and a. I have 4x and a. I have 2 and 2. And then the functions match as well. Sine, sine, cosine, cosine. So this one, we can say that a equals 4x. So sine of 2 times 4x. Hang on. Sine of 2 times 4x equals 2 sine of 4x cosine of 4x. And then the left side, we just want a single trig function, so that's sine of 8x, and that's all I'm looking for is the single trig function. Letter B. Cosine squared of 1/2 a minus sine squared of 1/2 a. That looks like our cosine double angle identity. So here it is in generic or general form. Cosine of, oh, let me not use a, let me use x. And that's cosine of 2x. Okay, that's our basic cosine double angle identity. Well, let's take a look again. I have oops, sorry. I'm looking at the entire argument. So I have 1/2 a, I have x. I have 1/2 a, I have x. What about the functions themselves? I have cosine squared, I have cosine squared. I have sine squared, I have sine squared. So everything matches, except that, let's be careful here, green, that x equals 1/2 a. That's the substitution we're making. Okay, so when I do that, I have cosine, so I'm going to bring this down. I want one single trig function. Cosine of 2 times 1/2 a equals cosine squared of 1/2 a minus sine squared of 1/2 a. Okay, and we're looking for just a single trig function, so this part just becomes cosine of 2 times 1/2 is 1, so it's just cosine of a. So all of this just simplifies back down to cosine of a. Okay, letter C. Sine of 5/2 x, cosine of 5/2 x. Well, let's stack it on top. I have 2 sine of a cosine of a, and that equals my double angle identity of sine of 2a. Okay, this one's a bit trickier, but totally doable, folks. I'm going to do it like this, okay? So first I'm going to look at the arguments themselves, right? So the arguments of each trig function, 5/2 x is a, 5/2 x is a. Okay, so I see those match. The functions themselves match, sine and cosine, sine and cosine. I have this 2 out in front that I'll take care of later. First, let's take care of the arguments so we're not getting confused with what goes where. All right, so let's do this. So I'm going to say a equals 5/2 x. Okay, let's make our substitution. I have sine of 2a, oops, sine of, let's make that substitution, sine of 2 times 5/2 x equals, well, let's make the substitution exactly as it's shown here. I have 2 sine, well, a is 5/2 x, so 5/2 x cosine, again, of 5/2 x. Okay, here's the problem I have is, I'll highlight it here. I have this 2 out in front, but here, where's the 2? There is no 2 in the original expanded version. So what can I adjust both sides by to get rid of that 2? And I say that in quotation marks, get rid of it, or account for that 2 so that we match our original identity. Well, what if I multiply both sides by 1/2? So 1/2 sine of, let's simplify this argument here. That's 1/2 sine of 5x equals 1/2 times 2 sine of 5/2 x cosine of 5/2 x. Okay, when I multiply both sides by 1/2, what ends up happening? Well, that just becomes 1. I'm going to leave the other side alone. Oops. And we're done, right? So I'm going to put a box around the simplified in terms of a single trig function. There it is. And this part right here, let me highlight it in dotted line here. This part right here doesn't match our original. Sure does, right? So take a look right here. Okay, letter D, example 5. We're going to continue writing expressions as a single trigonometric function. So this one I have here, I know a lot of my double angle identities, or at least the sine version. This looks suspiciously like the sine version of the double angle identity. It starts with a 2 as the coefficient. So if I rewrite this as 3 times 2 sine of pi over 10 cosine of pi over 10, does that make it easier to see? So if that's okay, and then 3, let's do this. I'm going to put the identity right under it in generic form. So sine of A cosine of A. And it's obvious to me that A is going to equal pi over 10. So sine of 2A, sine of 2 times pi over 10 equals 3 times 2 sine of pi over 10 cosine of pi over 10. Well, I have this 3 out in front with my identity, so I'm going to put a 3 out in front here. Okay, and we need a single trig function, so that's sine 3 times sine of, that's pi over 5. So that is our single identity. Next one, 1 minus 2 sine squared of 3a. Well, right away, this one looks like my cosine double angle identity. Okay, just written in a different form. First thing I'm going to say is alpha equals 3a. Oops. So what happens? Cosine of 2 alpha equals 1 minus 2 sine squared of alpha. Let's take a quick look. Yep, that is our double angle identity. So wherever I see an alpha, I'm going to plug in a 3a. Okay, so there it is. This right side looks exactly like this part here, so I'm going to focus on this one, make a single trig expression or trig function. That is cosine of 6a. Next one. Cosine squared of 5 halves x minus sine squared of 5 halves x divided by 2 sine of 5 halves x times cosine of 5 halves x. Well, this looks an awful lot like two separate identities here. This is the cosine double angle identity, and this looks like the sine double angle identity. Okay, so let me look at the numerator first. Numerator. Here's my double angle identity in general form. Cosine of 2a equals cosine squared of a minus sine squared of a. divided, cosine squared of A minus sine squared of A. If I put in A equals 5/2 x, because I see that all over here, every single term, every argument. Okay, so that's cosine of 2 times 5/2 x equals cosine squared of 5/2 x minus sine squared of 5/2 x. I'm looking for a single trig function, so the numerator is just cosine of 5x. Okay, I'm going to hold on to that for a bit. Let's do the denominator. Like I said, that looks like the sine double angle identity. So in general, sine of 2a equals 2 sine of a cosine of a. The a value is 5/2 x, and that's equal to 2 sine of 5/2 x times cosine of 5/2 x. I want a single a single trig function, so I'm going to simplify the left side. That's the sine of 5x. Okay, so what I'm left with is cosine of 5x divided by sine of 5x. And let me just show it all together. Cosine squared of 5/2 x minus sine squared of 5/2 x divided by 2 sine of 5/2 x cosine of 5/2 x. So that's where we are. Let's simplify this down into a single trig function. Well, cosine divided by the sine, that is just a cotangent angle of 5x. Okay, next one, letter F. 2 tangent of 25 pi over 12 divided by 1 minus tangent squared of 25 pi over 12. That looks like our tangent double angle identity. So I'm going to say A equals 25 pi over 12. So my double angle identity looks like this in general form. 2 tangent of A divided by 1 minus tangent squared of A equals tangent of 2A. So let's do this substitution. 2 tangent of 25 pi over 12 divided by 1 minus tangent squared of 25 pi over 12. And that equals tangent of 2 times 25 pi over 12. And we want a single trig function, so that's tangent of 25 pi over 6. Next page. Simplify and determine the exact value for each of the following trigonometric expressions. So we can actually do this two ways, right? What's the sine of pi over 3? Sine of pi over 3, that's square root of 3 over 2. What's the cosine of pi over 3? That is 1/2, and that is square root of 3 over 4. Let's use double angle identities to evaluate this as well. Okay, so if I have sine of 2a equals 2 sine of a cosine of a, it looks like the a value is pi over 3, right? So let's say a equals pi over 3. Well, what happens? Sine of 2 times pi over 3 equals 2 times sine of pi over 3 cosine of pi over 3. But you notice out in front, there's no 2 value. So how do I adjust that for the 2 value? Well, I'm going to multiply both sides by 1/2. So on the left side, I get 1/2 sine of 2 pi over 3 equals, oops, this one, let me be more accurate here. That's 2 times 2 sine of pi over 3 cosine of pi over 3. So that's 1. And I'm left with sine of pi over 3 cosine of pi over 3. Okay, so that equals what we started with. So this is good. Let's further simplify this. This is 1/2 times, well, what's sine of 2 pi over 3? That's in quadrant 2. So that would be positive square root of 3 over 2. And then that is square root of 3 over 4. So does that equal what we had in the beginning? Sure does. Okay. Okay, next one. I have 6 cosine squared of pi over 8 minus 3. That looks like a cosine double angle identity, but the first thing I'll do, folks, is I'm going to make it look like this. 3 times 2 cosine squared of pi divided by 8 minus 3. Well, because all my cosine double angle identities, it starts with that 2 in front of the cosine squared term. Okay, so that is, hang on, yeah, this should be, if I'm factoring out a 3, folks, sorry about that, that should be minus 1, just like that. Okay, in fact, let me use some square brackets so we can, okay. All right, so I know that cosine of 2a equals, and I'm going to leave a blank here, equals 2 cosine squared of a minus 1. That's my cosine double angle identity. Okay, but I want to make it look like this ultimately. So I'm going to say a equals pi over 8. So if I plug in pi over 8, okay, and then I have 2 times cosine squared of pi over 8 minus 1. Well, I have this 3 out in front, so I'm going to bring this 3 down. Okay, so I brought the 3 down. Well, I need to adjust it by putting a 3 on the left side because I'm trying to get this into a single trigonometric function or an expression and then simplify it, right, and determine the exact value. Okay, so this side looks exactly like that. So let's focus on the left side here. That's 3 cosine of 2 times pi over 8 is pi over 4. And then 3 times, what's cosine of pi over 4? Cosine of pi over 4 is square root of 2 over 2. And then that equals 3 square root of 2 over 2. Okay, example 6. Determine the value of k if sine of 8 theta cosine of 2 theta minus cosine of 8 theta sine of 2 theta equals 2 sine of k theta cosine of k theta. What's going on here? So this looks like got a bunch of double angles. Also, that is the difference identity for sine. So what I'm gonna do here is I'm gonna look at it in terms of first. Let me write out my sine difference identity. So sine of a minus b equals sine of a cosine of b minus cosine of a sine of b. And then I'm going to say let a equals 8 theta and let b equal 2 theta. So I have sine of 8 theta minus 2 theta equals, well, when I fill this in, folks, I get exactly what I started with, right? So cosine of 8 theta sine of b, which is 2 theta. Okay, so that matches this part right here. That's step 1. I recognize it as a sine difference identity. Okay, now that I have it like this, right, so I'm going to look at it in terms of sine of, let's simplify this, 6 theta. And we said all of this equals this, right? So I'm going to substitute this right side for this expression. So 2 sine of k theta cosine of k theta. Okay, so if I rewrite the left side in terms of a double angle identity, sine of 2 times 3 theta, and I just rewrite the right side like this, let me rewrite the double angle identity on the left side. So that would be 2, so sine of 2 alpha equals 2 sine of alpha cosine of alpha. Okay? Alpha in this case equals 3 theta. In this case here, let me highlight it. I have k theta, I have a. I have k theta, I have a. So when I make that substitution, a equals 3 theta. So 3 theta, a equals 3 theta. Oh, let me do it this way. A equals 3 theta, and therefore a also equals k theta. So if I set the two of them equal, 3 theta equals k theta, k equals 3. Okay, here's a you try. You can pause it here, give this a try, and then unpause. Given tangent of theta equals -3/4, where theta is greater than or equal to pi/2, but less than or equal to pi, algebraically determine cosine of 2 theta. So first, let me draw this out. It's between pi/2 and pi, so that's quadrant 2. So I'm going to draw my right triangle here. -3/4. So tangent is opposite over adjacent, and this adjacent part, it's on the negative x side, I'm going to assign the negative value to the -4. Okay, so algebraically determine cosine of 2 theta. So cosine of 2 theta looks like this, folks. Let's see what we need. Cosine of 2 theta that is, here's one of the identities, cosine squared of theta minus sine squared of theta. So I need a cosine of theta, and I need a sine of theta. Okay, so I know if I use Pythagoras, this hypotenuse is going to be 5. It's a Pythagorean triplet, 3 squared plus 4 squared equals 5 squared. So the radius there is 5, or the hypotenuse is 5. Okay, so I need a cosine of theta. Cosine of theta is adjacent over hypotenuse, -4. -4 over 5. Sine of theta is opposite of a hypotenuse, so it's 3 over 5. So when I look at cosine of 2 theta equals, remember this can be represented as cosine of theta squared. This can be represented as sine of theta squared. Okay, so cosine of 2 theta equals -4/5 squared minus sine squared of theta, which is 3 over 5 squared. And that equals 16/25 minus 9/25. That is 7/25. So cosine of 2 theta equals 7 over 25.